So welcome to another lecture of digital control system. In this lecture, we will discuss a few numericals based on the shifting property of Z transform, and also we will apply the inverse Z transform in these numericals. So let us start with the first numerical as the statement is given here. So a second order discrete time system is given, which is expressed by the equation as mentioned in this statement. And it is also given that the system is relaxed, that is, the response is 0 for all the values of k less than 0. And the input to the system is some value which is 0 for k is equal to 0, and uh, 1 for k greater than 1, right? So we have to find out the response of the system, right? Now the response of the system is nothing but we have to find out yk, right? Now how will we find out yk? And this is the question now. So now there are some you know major points which we have to understand. The first is that the equation which is given is not for the delayed, it is not the delayed equation actually. It is the equation with the advanced samples, right? So the given equation is y k plus 2 minus 3 by 2y k plus 1 plus 1 by 2y k is equal to r k plus 1 plus 1 by 2 r k, right? So this is the equation, but this equation is for the advanced samples. As you can see, that is the present value and the advanced value, right? However, we have been given that the response is 0 for all the values of k less than 0. So that means we need to convert this particular equation into the relevant form first of all, and then we will apply the Z transform to find out the Z transform of the given equation, and then we will see that how we can find out the response yk of the given equation. Now we have to convert this equation into the delayed uh, into the equation with the delayed samples, right? So if we shift this equation by two samples, right? So shift the above equation by two samples, right? So if we do so, what will happen? The equation will become yk minus 3 by 2 yk minus 1, right? Now delay, uh, we are shifting, we are not doing the advanced shifting, we are doing the delay shifting, right? We are applying the delay shift, right? So it would be then plus 1 by 2 y k minus 2, right? And then it is equal to r k minus 1 plus 1 by 2 r k minus 2, right? So this is, let us some equation number 1, for example. Now what we will do is we will apply the Z transform on this particular equation, right? So we will have the Z transform of this equation. Now to get the Z transform, we need to apply the shifting property also, right? So we will apply the shifting theorem on the above equation, right? And we will apply the delay shift, right? So by doing so, we have yz then minus 3 by 2. So this is delayed by one sample. So we have z raised to the power minus 1 yz plus y minus 1. Now this is the reason that we had to convert this equation into a delayed equation, because we have been given that yk is 0 for all values of k less than 0. That is y minus 1 is 0, y minus 2 is 0, and so on, right? So if we apply z transform on this particular equation, we will not get these negative samples, negative values. In that case, we will get the positive values, the advanced values, right? But those, for those values, no criteria has been given here, and that is why we have shifted the given equation by two samples, right? Now why we have taken two samples rather, that is also a question, because the maximum advanced value that we have is two sample, right? Okay, so the z transform of this is given here. Then let us take the, so now for the next one, it is for this equation. For this equation we have here, right? It is z raised to the power minus 2 yz plus z raised to the power minus 1 y minus 1 plus y minus 2, right? And is equal to, so here also we will apply the shifting theorem to get the z transform. So it is uh, z raised to the power minus 1 rz plus r minus 1, right? And plus 1 by 2. So it would be z raised to the power minus 2 rz plus z raised to the power minus 1 r minus 1 plus r minus 2. Now this would be the equation, right? Now, in, let us say this is equation number 2, right? Now in this equation, these values, right? So let us see these values. These values will be 0. Why they are 0? These values will be 0. These values will be 0. This value is also 0. This is also 0, and this is also 0. Now why it is 0? Because it is given in the statement of the question. And also, as you can see, this input rk is 1 for k greater than 0, right? For equal to 0, for less than 0, again it is not given. So we will assume that for less than also it is 0, right? So that means for all the negative samples, right, the value of r and y will be 0. So now let us simplify this equation, right? So we will simplify the given equation. So on simplifying the given equation, we will get, we will write it here. So we have yz minus 3 by 2 z raised to the power minus 1 yz, and then we have a 0 value here, right? Then 1 by 2 z raised to the power minus 2 yz, and then we have 0 value, and then we have again 0 value is equal to z raised to the power minus 1 rz and a 0 value, right? Plus 1 by 2 z raised to the power minus 2 rz plus 0 and 0, right? So we can further simplify this one. So we have yz minus 3 by 2 z inverse yz plus 1 by 2 z inverse square yz is equal to z inverse rz plus 1 by 2 z raised to the power minus 2 rz, right? Now we can simplify it further. So we have 1 minus 3 by 2 z inverse plus 1 by 2 z inverse square into yz is equal to, we have z inverse plus 1 by 2 z inverse square rz, right? So this is, for example, equation number 3. Now we can further simplify this equation, right? So we will have yz is equal to z inverse plus 1 by 2 z inverse square divided by 1 minus 3 by 2 z inverse plus 1 by 2 z inverse square rz, right? So now this is, let us, equation number 4. Now if we multiply, right, sorry, we can say that yeah, multiply and divide the this equation 4 by z inverse square, right? So we will get yz is equal to z inverse plus 1 by 2 z inverse square by z inverse square divided by 1 minus 3 by 2 z inverse plus 1 by 2 z inverse square divided by z inverse square, so rz, right? So this will give me a new equation which is z plus 1 by 2. So we can simplify this equation, and on simplifying we will get this equation z square minus 3 by 2 z plus 1 by 2 into rz. So we have simplified this equation, right? Further we can factorize this, right? Okay, so this part can be factorized. So if we factorize this part, so we will get z plus 1 by 2 divided by so on factorizing we have z minus 1 by 2, and then we have z minus 1 rz. So this is, let us say, equation number 5. Now up till here we have not applied the rz, right? Now we will introduce rz here. Okay, now let us go back to the numerical, right? So in this numerical, as you can see, the value of rk starts from greater than 0, that is, let us say, first sample. Okay, sample number 1. So that means this particular sample rk is nothing but it is a unit step which is delayed by one sample, right? It is a unit step which is delayed by one sample. So that means if we draw this rk, if we draw this rk, so its value is 1 but not at 0. So at 0 it is 0, and here also it is 0, but let us say at 1 it is 1, right? And then again 1, 2, then again 1, then again 1, and so on up till infinity, right? So that means this particular rk is nothing, it is a unit step function which is delayed by one sample. So given input is rk, which is a unit step sampled delayed by one sample, right? Now if we take the z transform of this, so we'll get rz. So rz will be, it is delayed, so delay means one delayer will be there into, and unit step will be z by z minus 1. So this z will be cancelled out.
Charge. Power off.
So this z has been cancelled out, so you have rz here is equal to 1 by z minus 1, right? So this we will substitute in equation. Now the equation number is 5, so we'll substitute this in equation number 5, right? So we have yz is equal to z plus 1 by 2 divided by z minus 1 by 2 into z minus 1 square. This is, let us say, equation number 6. Now we can apply partial fraction here, right? So we'll apply partial fraction. So we can say that yz is equal to a by z minus 1 by 2 plus b by z minus 1 and plus c by z minus 1 whole square, right? So this is, let us, equation number 7. So that means z plus 1 by 2 divided by z minus 1 by 2 into z minus 1 whole square is equal to a by z minus 1 by 2 plus b by z minus 1 plus c by z minus 1 whole square, right? Now we can solve this equation for ABC, okay? So solve the above equation for the values of A, B and C. So on doing so, the values obtained are given as, so what are the values here? If we solve this, so A will be equal to 4 and B is equal to minus 4 and C is equal to 3, right? So we'll substitute all these values in the equation this, right? uh, or in equation this, right? So we can get yz is equal to 4 by z minus 1 by 2 minus 4 by z minus 1 plus 3 by z minus 1 whole square. So this is, let us, equation number 8. Now to get the solution, we will apply the inverse z transform on equation number 8, right? So to get the response yk, we will apply inverse z transform on the equation 8, right? So inverse z transform of yz will give you yk, right? So it is inverse z transform on 4 by z minus 1 by 2 minus 4 by z minus 1 plus 3 by z minus 1 whole square, right? So yk, now yk is equal to inverse z transform of 4 by z minus 1 by 2 minus inverse z transform of 4 by z minus 1 plus inverse z transform of 3 by z minus 1 whole square, right? So this is, let us, equation number 9. Now if you see here, uh, we need to convert this into a standard form so that we can get a standard inverse z transform of the given form, right? So to do so, what we will do, we will divide and multiply this equation by z, right? So if we divide and multiply the given equation by z, each part by z, so this will be the new equation, right? So we have 4z by z into z minus 1 plus z inverse 3z by z into z minus 1 whole square, right? Now we can further write this equation as z inverse 4z by z minus 1 by 2 minus inverse z transform uh, z inverse 4z by z minus 1 plus inverse z transform z inverse 3z by z minus 1 whole square. So we can take these coefficients outside. We can take all of them outside, right? So we will have 4 z inverse z by z minus 1 by 2, right? Minus 4 inverse z transform of z inverse z by z minus 1 plus 3 inverse z transform of z inverse z by z minus 1 whole square, right? Now, as you can see, we have a delayer here. This is what we call as, okay. So this is what we call as delayer. Okay, so that means this when multiplied with this particular function has delayed its value. So every function has been delayed, right? So now what will we get? After applying inverse Z transform, the response that is obtained yk is equal to 4. Now we have got a delayed sample. Now if you compare this, it is compared with z upon z minus a, and z upon z minus a, z upon z minus a can also be written as 1 upon 1 minus a z inverse, right? And if you apply z inverse on this, so it is the z transform of some a raised to the power k, right? But in this case, because we have a delayed z transform, so we have 4, and here the value of a is 1 by 2. So 1 by 2 raised to the power k minus 1. Now why it is k minus 1? Because we have one delayer here, right? Then minus 4, and here the value of a is this. Here the value of this is also a, right? So we'll see, right? Now here 1 raised to the power k minus 1, right? Plus 3. Now let us come to this one. Now in this, if you see this equation, so if we have a z by z minus a whole square, so the inverse z transform of this is, uh, it is, let us say, n a raised to the power n, right? Okay, but here if you see we have the same equation. So here the value of a is 1, right? So value of a is 1, but it is delayed, so we have k minus 1 samples, right? And number of samples, right? Into, now value of a is 1, so 1 raised to the power k minus 1, right? So we can open up this 4 1 by 2 raised to the power k minus 1 minus, now whatever will be the power of 1, it will always be 1, 4 into 1, right? Plus 3 k minus 1, and this is also 1, right? Okay, so we have 4 1 by 2 raised to the power k minus 1 minus 4 plus 3k minus 3. So this will give me uh, 4 1 by 2 raised to the power k minus 1 plus 3k minus 7, and this will be true for k greater than equal to 1, right? So this is the solution. This is how we can find out the solution. Now in this particular question, as you can see, we have seen the application of Z transform. We have seen the application of shifting property. We have also applied the inverse Z transform. So all these three concepts have been applied on a single numerical, and we have got the solution. So now we have uh, one more numerical, as you can see here. In this particular numerical also, the statement has been given. In this statement, we have uh, an equation which represents a discrete time system, but it has all the advanced samples, right? As you can see, the input is minus 1 raised to the power k mu k. So that is, this input will exist for greater than equal to 0, right? Because mu k is a unit step sequence, and it is 1 for k greater than equal to 0 and k less than 0, it is 0, right? And the initial conditions are also given, which are minus 1, y for minus 1 is 5, and y for minus 2 is 6, right? Now, from here, you can see that you will never get the negative samples for this particular equation. So that means you need to convert this equation, you need to transform this equation into the relevant equation so that you can get the negative values, negative samples, right? So the given equation is yk plus 2 plus 1 by 4 y k plus 1 minus 1 by 8 yk is equal to 3 r k plus 1 minus rk. So this rk is the input, yk is the output, right? So let us delay the above equation by two samples, right? So on doing so, we have yk plus 1 by 4 yk minus 1. This is, for example, equation 1, right? Minus 1 by 8 yk minus 2 is equal to 3 r uh, 3 r k minus 1, right? Minus r k minus 2. Okay, so this is equation 2. Now we will apply the z transform on this equation, right? So we'll apply z transform here. So the z transform will give us yz is equal to 1 by 4, not equal to, sorry, plus here, not equal to, it is plus 1 by 4 y, so z inverse yz, and plus y minus 1 minus 1 by 8 z inverse 2 yz plus z inverse 1 y minus 1 plus y minus 2 is equal to 3 z inverse 1 rz and plus r minus 1, right? Minus, then you have z inverse square rz plus z inverse 1 r minus 1 plus r minus 2, right? So uh, this equation has been obtained by applying the delay shift theorem on equation 2, right? So this is what we have got. Now the values of y minus 1 and y minus 2 are already given in the statement. However, this is 0 and this is also 0, right? And this is also 0. Now why it is 0? Because your input is, rk is 0 for k less than 0. So it is given in the statement, right? Because this mu k is a unit step function, and because it is a unit step function, so it is 0 for all the values of k less than 0. Now we can simplify the equation further. So we have mm, yz plus 1 by 4 z inverse yz, and we have y minus 1. So y minus 1 is 5. It is given in the statement of question. Minus 1 by 2 z inverse 2 yz, and we have z inverse 1 5, right? And then we have plus, it is minus 6 given to us. Then we have the right hand side, so z inverse 1 r z plus 0, right? So uh, plus z inverse 2 r z, and then we have 0 values here, right? So we can further simplify this one. Y z plus we have 1 by 4 z inverse y z plus 5 by 4 minus 1 by 8 z inverse square y z. So on simplifying the equation, we have got these equations, right? So in this equation, we have taken yz as common. Now 6 by 8 plus 5 by 4 is 2, right? And then this equation has come here, and we have simplified these equations, right? So we're going to further simplify this as we'll take all these other sides, right? So 3z inverse minus z inverse square divided by 1 plus 1 by 4 z inverse minus 1 by 8 z inverse square rz, and then we have plus 5 by 8 z inverse, and we have uh, minus 2, right? And then we can write this as LCM, 1 plus 1 by 4 z inverse minus 1 by 8 z inverse 2, right? So this is, let us say, some equation number, for example it is 3. Okay, so we'll take it as 3. Now if we we can divide this equation by z inverse square, and so we can get this equation as a simple equation, which is uh, you know uh, we can get 3z minus 1 divided by z square plus 1 by 4z minus 1 by 8 into rz, and this here can be written as minus 2z square plus 5 by 8z, and then we have z square plus 1 by 4z minus 1 by 8, right? So this is, let us, equation number 4. Now rk is equal to minus 1 raised to the power k mu k, right? And mu k is 1 and 0, as it is already given for k greater than or equal to 0, and 0 for k less than 0, right? So if we take the z transform of rk, z transform of rk, so it is summation k is equal to 0 to infinite minus 1 raised to the power k z raised to the power minus k. So whatever is the power of this, so it will always be, uh, so let us take it like this. We'll write it like this. So k is equal to 0 to infinity, so we have minus z inverse raised to the power k, right? So so the z transform of this would be 1 upon 1 minus z inverse, right? So this will give me z upon z plus 1. So rz is this. So we will substitute this in equation number 4, right? So substitute rz in equation 4, right? So we have yz is equal to 3z minus 1 divided by z square plus 1 by 4z minus 1 by 8 into z by z plus 1, right? And then we have plus minus 2z square plus 5 by 8z divided by z square plus 1 by 4z1 minus 1 by 8. Now we can simplify this equation to get the solution. So we can take the LCM here. By taking LCM, so we can get yz is equal to, so on simplifying this equation, we have got this one. So in this, we will factorize this particular part and we have got this one. So now we can apply the partial fraction on equation 5, right? So we can write yz is equal to a by z plus 1 by 2 plus b by z minus 1 by 4 plus c by z plus 1. So this is, for example, equation 6, right? So we can further solve this equation and we can find out the values of ABC. So this equation number 6 has been solved using the partial fraction method for ABC, and the values of ABC as obtained are given here. So we'll substitute these in equation 6, right? So yz will be now we can make this equation so as yz by z, in fact. So we can take one z common out of here and one z will be taken common here, so it will be, it will go into the denominator of yz, right? So we have yz by z is equal to uh, we have 9 by 2 divided by z plus 1 by 2 and minus 1 by 10 divided by z minus 1 by 4 minus 32 by 5 divided by z plus 1, right? So we'll multiply this z here, here and here, right? So we have yz is equal to 9 by 2 z upon z by plus 1 by 2 minus 1 by 10 into z upon z minus 1 by 4 minus 32 by 5 into z upon z plus 1. Now, this is, let us say, equation number 7. So to obtain yk, apply inverse z transform on equation 7. So inverse z transform of yz will give you yk. So it is inverse z transform of this one. So we'll apply it on each part, z upon z plus 1 by 2 plus minus z inverse 1 by 10 z upon z minus 1 by 4 minus z inverse 32 by 5 z upon z plus 1, right? So this is how we can find out the inverse z transform, right? So now if you see in this equation has the standard formation as it is, right? So z inverse of a standard form z upon z plus a is actually a raised to the power k u k or mu k, sorry, right? That is for k greater than equal to 0, right? So it has a standard form itself, so we need not to apply anything else. So yk here is 9 by 2 z inverse, any inverse z transform of z upon z minus z upon z minus a. Sorry, see, this is z upon z minus a. You are right. So z upon z minus a is a raised to the power k mu k. So we will convert it to that form. So z minus minus 1 by 2, right? We'll write it like this. Then we have minus 1 by 10 inverse z transform of z upon z minus. It is already negative, so we don't have to worry about this. Then we have minus inverse minus 32 by 5, right? Inverse z transform of z upon z minus minus 1, right? So in this case, this is the a value, this is the a value, and this is the a, right? So yk is 9 by 2 minus 1 by 2 raised to the power k, right? Minus 1 by 10, and my this is 1 by 4 raised to the power k, minus 32 by 5 minus 1 raised to the power k, and it is mu k, because the given response will always be for the sample k greater than equal to 0. So this is the answer for the given statement, given question. So as you can see in these two numericals, we have seen that how to apply the shifting property, how to find out the z transform, how to find out the response using inverse z transform, and that to using partial fraction method. So this is it for today's lecture, and thank you so much.